Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 2, Part A. Question 1 of Part A says, derive the time-dependent heat diffusion equation for a uniform linear bar assuming constant thermal diffusivity. The first thing we are going to do is come over here and draw out the situation. So we have a bar, and we're going to say that this is X. We have position 0, position 1. We're going to call this the positive X direction. In this bar, we're going to take a slice. We're going to call this slice dx. Now to evaluate the heat diffusion through this bar, we're going to start with an energy balance. Energy balance, we're going to have our rate of change, in this case thermal energy, is equal to our energy in minus our energy out. So if we look at our energy in, what we're really looking at is the heat flow on the left side of the slice in the bar that we're going to call it heat flow at position X, with our heat flux. So we're going to start with our thermal conductivity times our area, and then times, of course, our temperature gradient, the driving force of heat transfer. And this is going to be evaluated at position X, call this X prime. And so that's our energy in. And for our energy out, that's the heat flow on the right side of that slice. So we're going to have our heat flux at X prime plus dx. And I'm going to use that same equation. Thermal conductivity is the area of heat transfer times the temperature gradient evaluated at X prime plus dx. That's our energy out. Now we need our rate of change. So we're going to start with this change in temperature. And what we want to get to is thermal energy. So as we discussed in other videos, to get there, what we need to do is multiply this temperature by mass times our heat capacity. But we don't really want to use mass in this case, so we're going to take that and say that density times volume is the same thing as mass. But in this case, we are working with area and some length term, so we can take this and turn it into area times dx, this little slice here. So erase that and substitute this in. So we're going to have rho times area, scooch it over a little, times dx. And this is equal to our energy in, which we expressed up here, minus our energy out. Of course, a minus times a negative sign makes a positive, so we need to change that sign there. Now we're going to make a couple of assumptions. So our first is going to be that the area is constant, so we can go ahead and just cancel out that term across the board. Next, we're going to assume that our K value is not dependent on a certain temperature, so we can go ahead and factor these K values out. And then finally, we're going to divide by our constants, so our density and our heat capacity to isolate the dt value. So what we end up with is K over rho times P times Tx Tx. And finally, we're going to divide across by dx because we're going to be taking the second derivative. So what we end up with is dt dt equal to k times rho, or divided by rho cp times our second derivative. Then the final step is just identifying that these groups of constants here are our thermal diffusivity. So we're going to assign that to the variable alpha. Just rewrite that equation. We are all set. Now we are ready to move on to question 2. This says express the heat diffusion equation from part A1 as an algebraic equation via backward differencing. Head back over here. And again, we're going to draw out the situation. So we have that same bar, but this time, instead of just making one slice, we're going to divide it up into multiple sections. We're going to pretend that they're all equal in size, and we're going to assign J as the variable for position. So we're going to have 1, 2, 3, all the way to n number of blocks. And one of these blocks is going to be our change in position. So now we can go over and define x as that change in position times what position we're at, almost like a counter. And then we're going to do something similar for time. So we're going to say that time is equal to the change in time times n, which is just a counter. Now, what our goal is to take this equation here, the bottom, and put it into algebraic form. So first, we're going to look at that dt dt variable. So change in temperature over time. And what we can do is say that temperature at position J at n plus 1, so the next time step, minus the temperature at that same position at the current time, so that's the difference in temperature, over delta T, which is change in time. So we have our change in temperature over our time step for change in time. Now next we have that second derivative, so we have T over x. Now for this one, what we want to do is look at the temperature. Well, first we want to look at the temperature to the right, so we're going to say J plus 1, so the next position over at some time, minus the temperature at our current position at that same time over that change in position. Now that was that's just the derivative to the right. So now we need to do the derivative to the left. So this time we're going to start with that temperature at some position at some time, minus temperature at the previous position at that same time, again, over delta x. Now, we need to make this into our second derivative, so all we have to do is divide the whole thing by delta x. Now all we need to do is substitute these values in to the equation we had here. So dt is this value here, and that's going to be equal to, forget our alpha, our constants, and that's our thermal diffusivity, times this second derivative. Perfect. Now we just need to isolate our TJn plus 1. So to do that, we're going to multiply across by delta T and add that TJn. We're going to have TJn plus 1 equal to alpha times, let's put TJn there first, plus alpha, or delta T. And now if we look here, we have these delta x's over delta x. So we can just take that, and we know that's going to be squared. We can take that whole thing and multiply by all our temperatures. We have TJ plus 1 n, and now we have 2 TJn's, so minus 2 TJn. It's TJ minus 1 n. There we go. And just like last time, we can look at this value here and assign it a new variable, and we're going to call this one R. Next, we can move on to question 3, which states, simulate the time-dependent response of a uniform bar initially at 20 degrees Celsius after its ends are raised, then maintained at 50 and 80 degrees Celsius respectively. Discretize the bar into 100 sections and show the simulated result for R is equal to 0.5 and R is equal to 0.501. So to start, as always, we want to import our libraries. So import numpy as np, and from plotly.subplots import make underscore subplots. Then we want to define our parameters. So we're going to start with an R value of 0.5. Then we're going to make 100 sections in our bar. Next, we need to set up our array of temperatures, so np.full, and then we're going to set each of those to 20 degrees Celsius. Now we want our initial section, so the end, to be 50 degrees Celsius, and the opposite end, the final position, to be 80 degrees Celsius. Now we're ready to set up our plot. So it's equal to make underscore subplots. Our x values are going to be position, so n range n. Then we want to make our scatter plot, underscore scatter. Like I said, x is position, y is obviously our temperatures, and we want our mode to be lines, and our name to be 0. Now we want to make a loop, so for I in range, go with 50,000. We need to update our t value every time, so we want this to be for our in-between sections, so 1 to -1. And now this is equal to that equation that we derived in the previous part. So that is T1 1 plus R times that Tj plus 1. We're going to go from 2 on. And then that was minus 2 times Tn, so that's that 1 to -1. And then plus Tj minus 1, so to -2. I did notice a small error here. Previously I had this, oops, that's very big eraser, as a negative sign. I forgot to carry through the negative from over here. So this should actually be a plus sign. So now this equation is correct, and we've also made that correction here in the code. So this should work. Now we have this going through 50,000 times, so we don't really want that many lines. So we're gonna alter that so that we don't have so many. So if for every 1,000 steps, we're gonna have a drop line, and we can just steal this little bit of code right there. If we're gonna change the name to this, and then we want to see the plot. Perfect. So this is what it looks like at R is equal to 0.5, kind of what you would expect. You can see the temperatures changing, but the ends still being 50 and 80 degrees the whole time. Now we can take a look at what happens when we change this R value to something above 0.5. You can see we have these big oscillations here, and this just demonstrates the instability of this equation that we're using. Moving on to question 4, the problem statement says, using von Neumann stability analysis, explain why simulation results are unstable when R is set larger than 0.5. So we're going to start by rewriting out our differential, so we don't forget. First, we want to establish some boundary conditions. Our boundary conditions are that the temperature at position 0 at any time is equal to 50. The temperature at position 1 at any time is equal to 80, and the temperature at any other position at T is equal to 0 is 20. Now I'm going to write out an equation that says Tk is equal to negative alpha k squared times T xp times I k x. Now we're going to take the derivative of this equation, and that is going to give us negative alpha k squared tk is equal to alpha times dx times ikx. Next, we're going to take the second derivative, which is going to give us negative alpha k squared tk is equal to alpha times I kx I kx. And if we simplify this equation, we get negative alpha k squared tk is equal to negative alpha k squared tk. Now, this demonstrates that our original equation here is a solution for our differential equation. Now we can say that if we take this equation and multiply it by some constant, then this value would also be a solution to the differential. So we could say that t is equal to an infinite series of terms that are multiplied by some constant, like these are also solutions. So if we write that out as some constant multiplied by this tk, which gives us an infinite series of possible solutions. Now what we want to do moving forward is to find constants that apply to the boundary conditions that we have established so far. Moving forward, we are going to write this equation out for just one particular value, even though we know that this is actually a summation. So it's going to be t is equal to exp times alpha k squared t, say delta t n, because if you remember, we established at the beginning that t is equal to delta t n exponent times I k delta x, and this for the same reason, x is equal to delta x times j, the j in there, and we are going to pick this value to be t j n. T j n is equal to this. Just like that. Perfect. And now we want to look at tj plus 1 n. Now this is just essentially tj plus an extra j, right, which is this term here. So we can express this as e I k delta x times tjn. And for tj minus 1, we're going to do the same thing, except now this is going to be negative because we're subtracting 1 instead of adding. Now that we have this, all we have to do is go take these three values and plug it into this equation that we established in part B. So that is tjn plus 1 is equal to t, we should probably write this on the next page. tjn plus 1 is equal to tjn plus r times tj plus 1, which is this here, was minus 2 tjn plus tj minus 1 n. Our equation. Now we have a tjn with every term, so we can go ahead and factor that out, which gives us tjn plus 1 is equal to tj n 1 plus r times e I k delta x plus e to negative I k delta x minus 2. Now this here are two very important terms because we know that eix plus ei, or negative ix, is equal to cosine of x. So we can apply that here to these terms, which will get us n plus 2 n 1 plus r times 2 cosine k delta x minus 2. Then we can factor out the 2. And 1 plus 2r times cosine k delta x minus 1. Now we have this substituted in, and what we want to look at now is this term right here. And what we want to do is set this term in absolute value signs, and this is to prevent our k value from going negative and building on itself and causing the instability that we saw in part C. Absolute value. And another way of saying this is just that it has to be greater than or equal to negative 1. Or less than or equal to 1. Now we can subtract negative 1, which gives us negative 2 is equal to 2r times cosine k delta x minus 1 equal to 0. And now we can kind of ignore this side here because the largest value that cosine right here could ever be is 1, and then that 1 minus another 1 is 0. So inherently we already know that this is never going to be greater than 0. And that this x 1 and then we can divide both sides by 2, which gives us negative 1 over r times cosine k delta x minus 1. And again, we can look at this cosine term here, but we're going to look at it from the other side now. Now the smallest value that this cosine could be is a negative 1, and then negative 1 minus 1 is negative 2, so we can just replace that whole set with negative 2 since that's the most severe that those values could be, which gives you negative 2r. Now we can divide both sides by negative 2, which leaves us with 1/2, and we have to flip our sign there. Gives us r, and this demonstrates that r has to be less than or equal to 1/2.